Good day, my friends. Today I will be talking about the contour line method, which is a technique applied for the continuous space facility location problems when the optimal solution is infeasible. But before doing that, let me remind you about the single facility location problems. We can explain the single facility location problems by the discrete space facility location problems and the continuous space facility location problems. Discrete space facility location problems, we were able to use three different methods: the qualitative methods, the quantitative method, and the hybrid method. For the continuous space facility location problems, we can use the median method, the gravity method, and the white spot method. In the median method, we were using the rectilinear distance, gravity method, the squared Euclidean distance, and the white spot method, we have the Euclidean distance. Remember, for the continuous space facility location problems, we have a certain geographical area, and within this geographical area, the number of alternative locations might be infinite. Okay, so if we have infinite set of alternatives, sometimes our optimal location can be infeasible. So when we have the optimal location is infeasible, we need to apply the contour line technique. Before talking about the contour line, let me remind you about the distance matrix once again. As we said, the median method uses the rectilinear distance. So what is the rectilinear distance? Let's say we have a Cartesian coordinate. We have 2 points here, point 1 and point 2. The point 1 coordinates are x1 and y1. Point 2 coordinates are x2 and y2. And the rectilinear distance between point 1 and point 2 is the horizontal distance and the vertical distance that we travel. It means that we cannot travel directly from one point to another point through a shortest path. We have to follow a horizontal path and then the vertical path. So the rectilinear distance in this case will be, in absolute value, x2 minus x1 plus y2 minus y1 in absolute value again. Why absolute value? Because the distance cannot be negative. The Euclidean distance, on the other hand, is the shortest path between these 2 points. So it is x2 minus x1 to the square plus y2 minus y1 to the square under the square root. This is the Euclidean distance. It's the hypotenuse of the triangle here. And the squared Euclidean distance will be x2 minus x1 to the square plus y2 minus y1 to the square. And the difference between the Euclidean and the squared Euclidean distance is that we don't have the square root in the squared Euclidean distance. So let's go to the contour line. So let me explain what is a contour line. Well, once again, contour line is a strategy, is a technique applied when the optimal solution is infeasible. At this moment, I would like you to remember your high school geography class. In order to talk about the height of each height of a mountain, we were drawing some lines like this. So let's say this is our mountain, and let's say we have 3 different heights for this mountain. In this region, the outermost region, the height is 300 meters. So at this location, at this point, at this point, anywhere in this outermost region, the height is 300 meters. In the middle section, anywhere like here, here, and here, the height of this mountain is 400 meters, and in the innermost area, the height of the mountain is 500 meters. So anywhere in this area, we have 500 meters. So let's say if the optimal location is this one, this red star, however, this point is not feasible, then we have to find another point in this area and which will be feasible. It will be the same height. It's not the feasible optimal location. We are going to have another location. It will be feasible and it will give us the same height. Or in other words, we are going to find another feasible location that will give us the same total cost as the optimal location. That means within the same contour line. Now, when we go back to the discussion of the contour line method, I would like you to follow our previous example. Remember, we had 4 different departments. Each department coordinates and the weights are provided. The coordinates of department 1 is 10, 2, the weight is 6. Department 2 coordinate is 10, 10, the weight was 10. Department 3 coordinates are 8 and 6, the weight is 8. And Department 4, the coordinates are 12 and 5, and the weight is 4. In this particular example, instead of the weight of the second department to be 10, I would like to consider it to be 20. Okay? So let's apply the median method. Remember, in the median method, we were doing it separately for the x-coordinate and for the y-coordinate. So let's do the calculation for the x-coordinates. We have to order them from the smallest to the highest values of the x-coordinates. So smallest x-coordinate value is 8. For department 3, the weight is 8. Cumulative weight is 8. Then we have 10 for the department number 1. 6 is the weight and the cumulative weight is 14. Then for department 2, we have the x-coordinate value 10 again. The weight is this time 20. The cumulative weight is 34. And then for department 4, the x-coordinate, which is the largest value, is 12. The weight is 4. Cumulative weight is 38. In the median method, we had to consider the half of the cumulative weights, which is 38 divided by 2, which is 19. So we need to check the cumulative weights here on the right hand side column. When the value of the cumulative weights is more than, equal or more than 19. So 8 is smaller than 19, 14 is smaller than 19, 34 is greater than 19. So the optimal x-coordinate is now 10. Let's do the same for the y-coordinate. For the y-coordinate, the smallest value is 2 for department number 1. The weight is 6, cumulative weight is 6. Then 5 for department 4, weight is 8, cumulative weight is 14. Then 6, y value is 6 for department 3. The weight is 4 and the cumulative weight is 18. And the largest y value is 10 for department number 2. The weight is 20 and the cumulative weight is 38. So we are going to again check the half of the cumulative weights, which is 19 again, and compare it to the right hand side column, the cumulative weights, when this value is equal or more than 19 for the first time. So 6 is smaller than 19, 14 is smaller than 19, 18 is smaller than 19, 38 is greater than 19. So the optimal y coordinate is 10. However, 10 and 10 for x and y coordinates, we have department 2, which is already available there. So 10 and 10 location is infeasible. Why? Once again, department 2 is already there. Let me show you the initial question here. As you see, 10 and 10 are the coordinates of department number 2. So in this case, what we need to do? We need to apply the contour line technique. Now let's put our departments on the Cartesian coordinate. Please follow the black colors. Department 1 is located at 10 and 2. Department 2 is located at 10 and 10. Department 3 is located at 8 and 6. Department 4 is located at 12 and 5. The contour line method has an algorithm which tells us that we need to draw a vertical line through the x coordinate and a horizontal line through the y coordinates of each facility. So these blue lines, please follow these blue lines that I drove. These blue lines are passing through the x coordinates and y coordinates of each department. The blue color line, which is labeled as V1, is passing through, as you know, on the left hand side department, which is department number 3. The second vertical line in blue color is passing through department 1 and department number 2, and then the third vertical line passes through department number 4. Department 1 and department number 2, they have the same x coordinate, so the vertical line which passes through them will be the same. And then we are going to draw 4 different horizontal lines that crosses each department. So this blue line here is the first horizontal line that crosses department number 1. The second horizontal line crosses department number 4. The third horizontal line crosses department number 3. And the last horizontal line, number 4, crosses department number 2. Our algorithm says that label each vertical line as V1 starting from 1 to up to P, and a horizontal line HJ 1, 2 up to Q, where Vi is the sum of the weights of facilities whose x coordinates fall on the vertical line I, and Hj is the sum of the weights facilities whose coordinates fall on the vertical line J. So when we go to our Cartesian coordinate, we know that department number 3 is lying on V1. So what is the value for the department 1? What is the weight for the department number 3 is 8. So the vertical line number 1, V1, the value for V1 will be 8. On V2, the second blue line, vertical line, we have, don't forget, department 1 and 2. So what were the weights of department 1 and 2? 6 and 20. We need to sum these up. So V2 will be 26. On V3, we have only department number 4. The weight of department number 4 is 4. So V3 will be 4. And then we need to put the values for the horizontal lines. For each one, it crosses department number 1, so the value for H1 is 6. H2 crosses department number 4, the weight is 4. H3 crosses department number 3, the weight is 8. And H4 crosses the second department, where the value is 20. Then we need to set I and j equal to 1 and n0 and d0 to be summation of the weights, but negative summation of the weights. So we need to say that n0 equals to d0 and they equal to summation of negative weights. Ni, on the other hand, in our algorithm at step number 4, Ni equals to Ni minus 1 plus 2 times Vi, and Dj equals to Dj minus 1 plus 2 times Hj. So we need to calculate the values for N1, N2, N3, and D1, D2, D3, and D4. N0, as you know, was summation of the negative weights. So what was the summation of the weights? Remember, 38. So N0 and D0 in that case equals to minus 38. So Ni equals to Ni minus 1 plus 2 times Vi. So if we would like to calculate N1, it will be equal to N0 plus 2 times V1. Do we know the value for N0? Yes, this is 30 minus 38. Do we know the value for V1? Yes, we know the value for V1, which is 8. So we need to calculate the value for N1, which is minus 38 plus 2 times 8, which is equal to minus 22. N2 is actually N2 equals to N1 plus 2 times V2. So V2 was 26, N1 was minus 22, so N2 is minus 22 plus 2 times 26, which is 30. There's a typing mistake here. Let me correct this as minus 22. Okay. Then N3 is equal to N2 plus 2 times V3. So N2 was equal to 30 and V3 equals to 4. 2 times 4 plus 30, it means it will be 38. We are going to apply the same for the DJs. Well, in order to calculate D1, D1 will be equal to D0 plus 2 times H1. So we know the value for D0, which is minus 38. So D0 having a value minus 38 plus 2 times 6. 6 is the value for H1. So minus 38 plus 2 times 6, we are going to have minus 26 for D1. D2, similarly, will be calculated by D1 plus 2 times H2, and it will be minus 26 plus 2 times 4. H2 was 4, if you remember. And D3 will be D2 plus 2 times H3 so 2 times H3 is 2 times H3, remember the value was 8, so D2 was minus 18. So let me correct this, yes. So minus 18 plus 2 times 8 is the value for H3. So D3 will be minus 2. And lastly, D4 is equal to D3 plus 2 times H4. D3 we already calculated to be minus 2, and it will be multiplied by the value of H4, which is 20. So the value here should be 2 times 20, 40 minus 2, it should be 38. So there's a typing mistake here, I corrected it as well. And then we need to calculate the slope for each box. What are these boxes? Remember we drove the vertical and horizontal blue lines. Drawing these lines, we have here different boxes, as you see. So we need to find out the slopes of the lines that we can draw inside of each boxes here. And in order to do this, let's say that on the left hand side of the vertical line 1, we are going to draw another imaginary, but this one is imaginary, another vertical line, and call it as V0, and the right hand side of the vertical line number 3, we are going to draw another vertical line, imaginary, and call it as V4. So the green lines here, V0 and V4, these are imaginary, and they can be anywhere to the left hand side of V1 and to the right hand side of V3. Similarly, to the below of H1, we are going to draw a imaginary horizontal line and call it as H0, and above the H4, we are going to draw another imaginary line and call it as H5. So these are the boxes that we can have between the intersections of the horizontal lines and the vertical lines. So the contour line that I need to draw within these boxes will give me the feasible area. So in order to find out this feasible area, I need to calculate the slope for each box. So the intersection of V0 and H0 box is this particular one. And this is the 0, 0 box. V0 intersects with H1, and this one is called the 0, 1 box. Do you see the red color? 0, 0 and 0, 1. These are the boxes. Now, this is 0, 2 box. This is 0, 3 box, 0, 4 box, 1, 0 box. It's the intersection of vertical line 1, V1 and H0. This is 1, 1, 1, 2, 1, 3, 1, 4, 2, 0, 2, 1, 2, 2, 2, 3, and 2, 4 box. And on the right hand side boxes, 3, 0, 3, 1, 3, 2, 3, 3, and 3, 4. So the red colors here shows the labels of the boxes. Now, the slope of any line that I will be drawing in these boxes will be calculated by n minus ni divided by dj. In the above section, we calculated the values for ni's and dj's. So for the S00 box, S00 box is this one. The value of any line that we are going to draw, the slope will be minus 38 divided by minus 38, but don't forget about the negative sign at the beginning. So negative 38 divided by negative 38, we are going to have negative 1. So in this box, 0, 0 box, the slope will be minus 1. Okay, and the blue color minus 1 here shows the slope of 0, 0 box. In the 0, 1 box, we are going to divide n0 by d1. So this was n0 divided by d0, but this one is n0 divided by d1. d1 was, remember, 26. So minus 38 divided by minus 26 multiplied by negative 1, the slope for 0, 1 box will be minus 1.46. So 0, 1 box, the slope is minus 1.46. So any line within this box, the value will be minus 1.1. Any slope that I will be drawing in this box should have a value minus 1.46. So here again, this is n0 divided by d2. d2 was minus 18. So minus 38 divided by minus 18, minus 2.11. So in the 0, 2 box, the slope will be minus 2.11. And we are going to continue this for every single box here. So these calculations shows the calculation of the slopes for each box. I put this here in the blue color so that you can follow. Now, the next step here in our algorithm is actually to select the infeasible optimal location. What was that? 10, 10. And around this infeasible optimal location, we are going to choose any box. So starting from 10, 10, let's say in this box label 1, 4. In this box, we are going to draw a slope, and the value of this slope will be 0.58. So it's not going to be a steep slope. So starting from here around the infeasible optimal location, I'm going to draw a slope in the box 1, 4 with a slope value 0.58. So I'm going to start drawing it until I hit a vertical line or a horizontal line. So I hit the V2 line here, so I'm going to stop there. Starting from there, I need to draw in the box 2, 4 a slope which has a value negative 0.79. So it's a decreasing slope, so it should go down. Okay, so starting point is this point where I left, and I have to draw a decreasing slope, and I'm going to draw this slope until I hit another horizontal or vertical line, and I hit a horizontal line here, H4 line, and I'm going to stop here. And then in this box, forget about the others, in this box only in this box 2, 3, I need to draw a slope which has a value 15. So it should be a very steep slope. Okay, please follow the cursor here. The end point should be up here. Starting point should be here. So we need to draw a steep slope which goes up here. And then when I hit here H3, I'm going to stop, and I need to draw another slope here in the box 2, 2, which has a slope value 1.67. So it's a positive slope as well, it goes up. So I need to draw this. When I hit here on this vertical line, I need to stop, and I need to draw a negative 1.22 value slope here in the box 1, 2. So it's, look at here the cursor, it goes down. It goes down means it's a negative slope. And also when I hit the horizontal line H3, I need to stop. And also in this box, 1, 3 box, I need to draw a slope which has a value negative 11. So it should be going down. Remember the starting point. From that starting point up to here, I need to draw this negative slope. So this orange color shaded area gives me the feasible region. In this feasible region, we have the same total cost as the optimal location. So same total cost as the optimal location means that within this region, any point that I select will give me the same total cost as the optimal location. The optimal location was 10, 10, but it was infeasible. Now any point here in this shaded region will give me a feasible location, which gives me the same total cost as the optimal location. This was the contour line method. Thanks for listening. I will get back to you on another different topic on the next lecture.